an example of a continuous Fourier transform where our signal is aperiodic. So as you can see, we have a function that starts from 0, goes up to 1, and then there's this kind of, it's a discrete function. So the square wave drops down at this discontinuity and then flatlines at -5. So this signal does not repeat. It is aperiodic, but we can treat it, that's the beauty of Fourier analysis. You can treat it as an aperiodic signal as periodic over some period t. So the total time scale that I'm looking at here, if this is in seconds, this x-axis, is 2 seconds. So even though the signal is aperiodic, I'm going to treat it as periodic as it repeats. I'm assuming, or I'm going to kind of imagine that this signal is going to repeat after 2. So if I do that, I can do my same Fourier analysis that we've been doing previously. So let's go ahead and look at that now. So t equals 2 seconds. Then I know my delta f, my fundamental frequency, is 1 over t. I can solve those values here. I know that my y sub 1 is just equal to t. My y sub 2 is equal to -5 right there. And now I could go ahead and calculate my harmonic coefficient. So my a sub n is going to be equal to 2 over t. The integral times integrate my y sub 1 from t from 0 to 1 there, plus integrate, actually I need to integrate times cosine of 2 times pi times n times t divided by my period here. And I'm going to do the same thing. Take this one right here. I'm going to add it right here. And then I'm going to go to y sub 1 times y sub 2, actually. My limits of integration change. And get this value right here. So there's my a sub n. My b sub n is going to be very, very similar, with just the exception of, let's see here, I'm going to change to sine. So sine, 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 and there we go. So if I want to calculate my c sub n, or actually I can just do this, create a table. I'm going to, actually, real quickly, I'm going to steal a little line of code. It's not plagiarism if you made the code. So let me grab this here, this right here, and then I'm going to go from, actually I'm going to go ahead and get this here. So I want to function as I'm going to do 10 harmonics, I times delta f, 10 harmonics, square root, again, this is my c sub n. Let's see what we've got here. And this is our frequency spectrum. So, again, this makes sense because our fundamental frequency is what? Half, 10 harmonics. That should be our maximum frequency. And I could also calculate, actually, let's zoom out here so that people can see and confirm their answers later. So there's my harmonic coefficients, or actually my frequency spectrum. And then now I could also plot my Fourier series. So I know that my a sub naught is going to be equal to, I'm not going to plug in for n equals 0, but I'm just going to kind of plug in here. I know my b sub naught is always going to be 0, so I don't have to worry about that. And then now I just need to do y sub 2, get rid of this cosine, because cosine of 0 is 1. So there's my a sub naught. And then now I could just plot this. And you see it's a pretty nice function. So 10 harmonics, what happens if I go to 100 harmonics? Let's just make sure everything is right in the world. So let's look here. That looks a lot better. And if I do only 5 harmonics, a lot worse. So this is the beauty of Fourier analysis, is even if you have an aperiodic signal, you could treat it as periodic over this period kind of t. So we can imagine that it'll repeat into infinity. Maybe it will, maybe it won't, but again, you could still get, we can analyze that aperiodic signal and get information about the frequency spectrum. And that's kind of the beauty of this. So, hope that helps, and good luck on Fourier analysis. It's not too scary, believe me. Have a good one. Bye.